Hello everyone, I am going to explain question number 17 from miscellaneous exercise of chapter 7 from 12th class maths. So question number 7 is verify the Lagrange's theorem for the following function. So Lagrange's theorem, first I want to explain. In Lagrange's theorem there are two conditions. First condition is the function should be continuous in the closed interval. The second condition is function should be differentiable in the open interval. If any function is satisfying these two conditions, then there must exist a point C belongs in the open interval such that f dash C is equal to function's value at upper limit minus function's value at lower limit divided by upper limit minus lower limit. So this is the theory of the Lagrange's mean value theorem. So the Lagrange's mean value theorem has only two conditions. First two conditions are same like Gauss theorem, continuity condition, and second is differentiability condition. So we'll proceed. First I wrote the function and it's a polynomial function, but I opened it so that easily I can differentiate it. So here I wrote fx is a polynomial function, and then we have to mention whenever we get a polynomial function, always we have to write down this statement. Polynomial function is continuous as well as differentiable for every real number. After writing this statement, we can conclude like this: fx is continuous in the closed interval and fx is differentiable in the open interval. Intervals whichever is given to you. In continuity, always closed intervals is write down, and in differentiability, always is write down the open interval. Now both conditions, Lagrange's mean value theorem have only two conditions, so both conditions is satisfied. So there must exist a point C such that, so this is the Lagrange's mean value theorem's conclusion, that f dash C is equal to function's value at upper limit minus function's value at lower limit divided by upper limit minus lower limit. So here I wrote function. Since whatever we want in this equation 1, first I calculated that and then I replaced it in equation 1. So first I wrote the function, then I calculated the f dash x. F dash x means first order derivative. So I differentiated it with respect to x. That gave me this answer. And after differentiating, since we want f dash c, so f dash x, wherever x is there, I replaced it by c. Then we want, so f dash c we obtained. Now what we want? f4 and f0. So for that, first I wrote my original function without opening the bracket because that is more convenient. Then I wrote f4, and to get f4 wherever x is there, I replaced x by 4. That gave me the answer 6. Then f0, that again gave me the answer minus 6. So I obtained whatever I need in equation 1. So I replaced all the values in equation 1. After replacing it, I obtained like this. Here I simplified, I done the plus minus, and I divided this 12 by 4, so I obtained here 3. This 3 I shifted in the left hand side. That gave me the quadratic equation, and since factorization is not possible, so I took the help of quadratic formula. I hope quadratic formula you still remember, which we had done in 10th class. So quadratic formula I used here, that is minus the coefficient of c plus minus coefficient of c square minus 4 multiplied by a into c. So like that in quadratic formula I substituted the values, and after using the quadratic formula I obtained like this, and here 48. So 48 I factorized and I took whatever I take common. So 4 root 3 I got answer. Now root 3 value I replaced by 1.732 because I want to check whether which value of c belongs in the open interval. So for that I need exact answer. That's why root 3 value also I replaced. I multiplied by 2. First I had done the addition and then divided by 3. So that gave me 3.154, and I checked whether it belongs in the open interval. So it's belonging, of course. Then I took the minus sign in middle and I subtracted, and that also belongs in the open interval. So conclusion is for both plus and minus value of c, for both value of c, the function is satisfying this condition. So Lagrange's mean value theorem is satisfied. So I hope this question is clear to you. Now we'll move to the B part of the same question. In B part, again we have fx as a polynomial function only, but here we have two constraints. For x less than 2 we have this value of the function, and for x greater than equal to 2 we have this value of the function. So whenever a polynomial function is treated like this, we have to proceed. It's a unique question. So in this we have to write down, so both are polynomial. So for x, whatever constraints are there, just write down. Not for equal to, only for less than and equal to, just write down. The function is continuous as well as differentiable, but we have to check for the equal to. Means for x equal to 2, only we have to check the function is continuous or not, continuous differentiable or not. So first we check the continuity of fx at 2. So what I said to you, how this question is different from others. Here the fx is a polynomial function, but it is splitted for two conditions. First, x is for less than 2. The second is when x is greater than equal to 2. So students, whenever we get this kind of question, in that for x less than 2 and for x greater than 2, we don't have any problem. But for x equal to 2, we can't write like this. We have to check it. Actually, we have to check whether the function is continuous or differentiable or not. So I checked it one by one. Continuity of fx at 2. So continuity we have to check. So first I wrote, for continuity we have three conditions. First, function's value at 2, then left hand limit, then right hand limit. So for first fx at 2, so f2 is equal to 5 minus 2 equal to 3. Then left hand limit, for left hand limit 2 minus 0. So this we had done already in chapter 6th. So limit s tends to 0. Then this 0 we have to replace by h. So 2 minus h means it is less than 2. So when it is less than 2, that time what is the function's value? 1 minus x. So this in 1 minus x we will replace x value as 2 minus h. So here 1 minus x, instead of x we replace with 2 minus h. So when we open it, we get here 3 and h value is 0. So h value got 0. So 1 plus 2 is 3. Then right hand limit at 2. So for right hand limit we have to do plus 0. Then replace it by h, where h tends to 0. And now 2 plus h means it's greater than 2. So when x is greater than 2, that time function's value is 5 minus x. So in 5 minus x, we will put the value. Instead of x, it will come 2 minus h. Now when we will open it, we will get again 3. So what we found is f2, then lower limit and upper limit. Both are equal. Since all three values are equal to each other, so we can write function is continuous at 2. Now we have to check function's differentiability at 2. So left hand derivative at 2 is this. Now here we have to put the values of f2 minus h and f2. So 2 minus h means less than 2. So for less than 2, what is the value of function? For less than 2 we have 1 minus x. So in that we will put the value. So here we will replace the value. So 1 minus h. So 1 minus h, I directly open the bracket, and f2 I already calculated before, that will give you 3 answer. That's why here 1 plus 2 is 3. So 3 minus 3 is 0. So we will remain with minus h and minus h, that will cancel each other. So we will get here 1 answer. Now right hand derivative at 2. So in right hand derivative the formula is limit h tends to 0, 2 plus h, then minus f2 upon plus h. So this is the formula of right handed derivative. So here 2 plus h is there, so it is greater than 2, so we will use the formula x, 5 minus x. So instead of x, what will come here? 2 minus h. Then f2 value, f2 means when it is equal to 0, that time also function's value is 5 minus x. So instead of x, we will write down here 2. We will open all the brackets, and here when we check it properly, we will find that 5 minus 2 is 3, then 3 minus 3 is 0. So we will obtain minus h upon plus h. That will cancel each other. That will give us that left hand derivative at 2 and right hand derivative of function at 2 are not equal to each other. So we conclude that fx is not differentiable at 2. Since function is not differentiable at 2, that's why we will write down that the second condition of Lagrange's mean value theorem is not satisfied. So for given function Lagrange's theorem is not applicable. So I hope this question is clear to you. So in this question, student, a polynomial function is split in two parts, and for x less than 2 and for x greater than equal to 2. So in this situation, for x less than 2 and for x greater than 2, we don't have any problem, but for equal to 2, we have to actually prove that whether the function is continuous or differentiable or not. So when we started to prove it, we found that the function is continuous at 2, but the function is not differentiable at 2 because left hand derivative and right hand derivative are not equal. And since the second condition of Lagrange's mean value theorem is not satisfied, that's why for given function fx, Lagrange's mean value theorem is not applicable. So I hope the both parts of question number 17 are clear to you. And if you have any problem, you can write in comments so that I can clear out. Thank you.